Welcome back to learnpiezo.org. Today we're actually going to verify the equation we derived relating the strain and the deflection on a cantilever beam aimed at determining the voltage developed on a unimorph which has a piezoelectric layer laminated on the top, sort of to determine its the voltage developed when you push down on it. To use it as a sensor or perhaps an energy harvester. So we developed a couple of equations. You can find that in the last video of this section, part 1. But essentially we got to the point where we related the strain, the maximum strain, with the deflection, as seen as in this equation, and also the deflection related to the maximum stress as well. And then we derived using the average strain, which would be half, to be equal to the voltage if you multiply the thickness and the piezoelectric G constant G31 and the S coefficient SD11. So let's go into simulating that using FEA analysis. This is sort of just an introduction. Probably in other videos we will introduce a finite element analysis in more detail. So we're going to be using a program called Mecway, and this is a finite element analysis software, and it's similar to ANSYS or COMSOL, except that it's a lot cheaper. It's $300 for a professional version to do commercial work, whereas if you want to do commercial work legally with ANSYS or COMSOL, you would have to pay over $10,000, and depending on how many packages you got, multiples of that. But this is $300, so if you can actually get away with using, not get away, but if you can actually use this in an intelligent way, and many factors, even for development of piezoelectric materials, even though the support for piezoelectric materials directly in this program is not mature, however, being smart about how you define parameters, you can use this program very effectively to model piezoelectrics. And also, you should not, use the crack version or use the student version or the evaluation version for actual commercial work, because that's sort of illegal and it sort of doesn't provide support for people developing programs such as Mecway or perhaps an open source alternative. It sort of stifles that. It's sort of immoral in some ways as well. Anyways, enough about that. Now we're going to draw that cantilever beam, in which we're going to use it to analyze the relationship between displacement, tip displacement, and applied force. So we're going to start by drawing nodes, and this is basically going to outline the circumference of our cantilever beam. So we're going to draw one point at 0, 0, 0. And we're going to have it to be 1 millimeter thick, so let's just draw the y-axis 1 millimeter thick. The length is going to be 20 millimeters. And finally defining the last point, 20 by 1. If we then zoom in appropriately on the structure, we have what we see here. We have 4 points. So now what we do, we're going to define a element, we'll say. So we'll define what we'll call a quad 4 element, which has 4 corners. So first, and what we do in FEA analysis or FEA, we define, oops, that should not have been there. Let's just delete that, sorry about that. So basically the points which are going to use 1, 2, 3, 4. You could have selected them by clicking on it as well. Okay, so let's just do it in a different way. Okay, let's just choose this 1, 2. This should order you gotta go in. Okay, so we have this element here. Now what I want to do is I want to divide it up into smaller elements. The way FEA analysis works is that it basically takes your structure that you drew and it chops it up into many different small parts, which then it combines those using Newton's equations or other dynamic equations. And basically by connecting these individual elements, so hence the term finite element analysis, you're able to come up with a final solution for complicated structures. In this case, we're just going to verify our analytical solution. to see how realistic it is. So we're going to be what we're going to call refining this, because this is just one element. We have to refine it into more a better axis. So this is going to be the lateral divisions, which we're going to write as 20, and the vertical divisions, which we're going to have as 10. So if you can see here, the lateral divisions, the vertical divisions. We have 20, we have 10 across here, and 20 in thickness. Since we only have 200 elements, we can do a little better than that. We're going to go to, again, you can't see the menu because of the way I analyze. So it's going to be right here. It's going to be mesh tools, refine, custom, and on the x-axis, let's say we want 20, and on the thickness we'll have 10. That looks like opposite. Sorry. There. So we have this this nice structure here. What we're going to have to do next is we can do a couple of different things depending on what we want it to, but we're going to define the boundary conditions, which is we're going to have a clamped, and we're going to have a force here, clamping here, force there. But what we're going to do is we're going to select this, which will allow us, this will allow us to select the nodes, this will allow us to select the faces. And because this is a 2D simulation, which we should change it from 3D now to static 2D simulation, we're going to be applying this now. Fix support. And obviously let's click select anything. So we want to fix that support, 10 faces, great. Then we're going to apply a force to this node right here. And we're going to apply a force in the negative y direction, a downward force. This looks a lot like a cantilever, doesn't it? The next step is what we have to do is we have to assign the material. In this case, we'll do a plate chill member. If you have an interest of simulating a 3D simulation using a 2D format, for example, if this is really thick and you wanted to know the effect of having a 3D simulation, then you would use plane strain. However, this is defaulting to plane stress model, and we're just going to write it as, since it's 10 millimeters wide. But we're not going to have a 3D. We're not going to have strain stress variation in the z direction. Okay, so that's the materials assigned. But we need to edit it, and we need to say it's isotropic. Defines parameters. So let's say 700 megapascals. Standard Poisson's ratio is 0.33. The density doesn't matter. It comes into play when you are doing a dynamic simulation. However, we're doing a static simulation, so it won't have effect. So we're just going to have it as 0. And okay. So we have our material defined, we have our shape defined, we have our mesh, which are the individual elements which the computer will be solving. We have our boundary conditions, we have a force here, we have fixed support there, and we press this button to solve. So if you want to take a look at the displacement magnitude, here it is. In the deformed shape, we see that obviously there's deformation going on here. On this side, it's clamped. And here, this plot over here tells us the displacement in millimeters. So depending on the thickness you specified in your materials, you're going to have a different displacement. So that's sort of important if you're looking for the magnitude. Unfortunately, we can't look at the strain. However, if you did a 3D simulation, what you can do is you can, if you want to do a 3D simulation, you can go to Options, you click Labs, and then if you did a 3D simulation, you can enable this. So I'll put strain on solid elements. However, we're doing a 2D simulation, so it's not available to us. But let's just take a look here. Let's look at undeformed, and we don't want to see the mesh here, and this is also not important. So basically we're seeing, if you can zoom in here, this is the X strain. So we sort of see a stress strain variation. We have approximately equal compressive and tensile stress on the top and bottom. The top is going to be tensile, the bottom is going to be compressive, the blue. So we have that many megapascals. So basically what we want to do is, let me just open a program here. This is go to a different program, the insert sheet. It doesn't make a difference to me. And we're going to basically define certain parameters. So if you go back to our PDF or whatever, we had this relationship between displacement and stress. So how can we get to the strain? Strain is just obviously the elastic modulus. The stress divided by the elastic modulus is going to be the strain. So anyways, so basically what we can do, we can either calculate the strain if we wanted to. So here on this we have these stress values, and usually the stress values on FEA programs, the maximum of the scale is going to be the maximum strain. Stress development is going to be at the fixing point at the top or at the bottom. So 9.281 megapascals, we have that number. So stress 9.218 e to the 6, that's mega, and that's what pascals will be the unit. The length we drew, the length is 20 millimeters, so 0.02 millimeters, and the thickness is 0.001 meter because it's a millimeter long. So having all these points, and what's the displacement magnitude? This displacement in y is going to be negative 3.314 millimeters. So displacement. What is it again? 0.00314 meters. So now we want to verify this equation, or to verify it, you're going to have to use this equation here. So the displacement equals the stress. Oh, and let's take a look at that Young's modulus. In the program we had set the Young's modulus to 700 megapascals. So in the program I'll have to send it to, so I'm going to write modulus to 700 e to the 6. Let's write as e 700 e to the 6. Alright, so newtons, newtons per meter squared, or pascals. Okay. Now what we're going to do, we're just going to chop some stuff. We're going to use a snipping tool here. I'll just take that with me to the program, the Excel sheet, and hopefully this program lets us drop it in pretty easily. Yes, it does. So basically I want to verify this equation. So the displacement, which should be this number here, is going to be equal to calculation. So calculated. Displacement, it's equal to the stress, or the maximum stress, multiplied by 2 multiplied by L squared divided by 3 times E, which is going to be here, times H, which is going to be here. And there you have it. The estimated strain displacement is 0.035, and the observed displacement is this. So what we just subtract it, just so we can get an idea of the error here. That's the error, this divided by that. So we have an error about 10%. And I've done this simulation with other parameters, and as we now, if we increase the mesh, So if you go back here, let me see the mesh again. If you go back here and let's format to there, and if you use a finer mesh, we'll be able to get a better result. So what happens so now if we use a better mesh, you can get, and you can do that using different ways. So for example, you can highlight here, and you can say refine the mesh. So we get an even finer mesh going on at this angle. So basically by increasing the mesh size, we can get a closer value, and also as we increase a longer and longer length with regards to the thickness, we'll also get better agreement with the results. But this gives us a good general agreement. We can have, within 20%, we'll be able to pretty well determine our stresses and strains. Keep in mind this is an analytical solution, so there are a lot of things in real life that are such as clamping conditions, which aren't considered in this 1D model. But I think we got pretty close, and this pretty much tells me that yes, I did my calculations correctly. This does work. There's an error here. I've done the simulation with a larger mesh and also a larger length to thickness ratio, and I got better results within about 5%. But for this example, we have this result, so we can say this equation is correct. So we want to when we want to move forward and use the average strain, which is the stress. So how can we determine the strain from the average strain? So the average strain, so we know from the Young's modulus that the stress equals the strain, which is x, multiplied by the Young's modulus. So if we divide the stress by the Young's modulus, so we take this divided by that, this is the maximum strain. So it's 0.013 or 13 millistrain. You can say 13 milli. That's the strain level we're seeing here. And the average strain is simply that divided by 2. There you go. So I hope you found some value in this basic FEA demonstration. The program again was MechWay. There are a lot more examples using this program. It's rather inexpensive for commercial applications. It's quite capable. It also has several other features which we may or may not go over, but some interesting ones for piezoelectrics, because we use piezoelectrics in resonance conditions. It's very interesting to look at the modal vibration to determine where you might want to place your piezoelectric materials, what the resonant frequency is, and that can get you a lot of data. Although it won't get you impedance data, it won't get you electrical analysis, but you'll be pretty well on your way to designing a reasonable transducer using just these analysis, and it sort of gives you a better it shows that you have a better understanding if you're able to solve problems with less tools, because sometimes no matter how much computing power, no matter how capable your programs are, it's only as capable as you are as an engineer. But this can be very sufficient for designing transducers. Thank you for watching. I look forward to any other questions people might have. All these questions which are being asked are from real people wondering how they can apply piezos in their situation, depending on how much knowledge what they know and what they don't know. They've asked questions, and I've tried my best to answer them. So I look forward to any other questions and further video posts. Thanks for watching.